All right. In the last video, we took a look at creating this nth Maclaurin polynomial. It was just a polynomial that was used to model a very complicated function that would otherwise be difficult to plug numbers into. And we're going to look here at example 3 at exactly this type of complicated function, maybe like a e to the x. We already modeled this before in previous examples, but now we're going to try to write out p0, p1, p2, and pn for e to the x. In fact, I might even go ahead here and write out, or we could think about writing out a couple more of these. We'll see how I do that in just a moment. All right, so let's see here. If I want to go ahead and start to build this polynomial, again, I can see that this is the formula for it up here. I just have to pick what power I'm going to stop at. But remember, that's what this little subscript here on the p in the front stands for. It's also important to keep in mind this formula right here for c sub n. And so I'm actually going to go ahead and copy that down on this page just so I can take a look at it as my formula for all my coefficients. So let's see what we got here. If I wanted to find p0, then that means that I'm going to, p0 of x, I'm going to have to go all the way up until n is a 0. Well, that's actually going to be a really short polynomial because that's just going to be the equivalent of just finding c0. But c0 itself is really easy to find again with this formula. It would say take 0 derivatives of the function f. Well, if my function f is right here, f of x is e to the x, then taking no derivatives of it is just e to the x. When I plug in 0, I get back 1. And then I divide that by 0 factorial, which in the last video we said would be the value 1. So my first polynomial here is just 1. And you can even see that down here in the picture on that purple line, right? That's modeling the graph of this blue e to the x. It just models really terribly. Notice that if I go to P1 and I construct this, I would need to find C0, which I already got, and then I would need to find the number that goes in front of x first, which is what happens when I plug in the number 1. So I'm going to get the first derivative of my function is e to the x, plug in 0, I get back 1. And so I'm going to get 1 over 1 factorial, which is 1. So I get 1 plus x. We already found that. That was our tangent line that we did back at the very beginning of the section. If I go to p number 2, then I'm going to stop once I get all the way up to the number in front of the x squared. Okay, again, not difficult to find. That would be c number 2. So I need the second derivative of my function. Second derivative e to the x is still e to the x. Plug in 0, you still get 1. And in the denominator, I would put 2 factorial, which is the same as 2. So boom, there's the quadratic. And we did that several examples ago as well. But notice if I kept stepping this up, I could easily find p sub n. I know that it would start exactly the same way. It would just keep going and going and going until I got all the way up to x to the power of n. I would just have to figure out the number that goes in front of that, the coefficient. So I would say, well, what happens if I plug in n? Well, here's kind of an interesting thing. No matter what derivative I take of the function e to the x, what is the answer always going to be? Well, yeah, no matter how many derivatives I take, this derivative is just e to the x. So when I plug 0 into any of the derivatives, I always get 1. And then I would just be over n factorial. So this would be the way that I could express this. Here's the cool part, is that it's totally possible that, again, I could rewrite this as a series. I'm going to have my series here have a counter of a k, and I'm going to imagine that that k stands for the different powers on the x's. So notice here, my highest power is n, and my lowest power is technically 0, because I have a constant at the front. And I know exactly then what each of these terms is going to look like. They each look like x to the associated power of k. So I'm going to start with x to the 0, then x to the 1, then x to the 2, so on and so forth, and I'll stop when I get to x to the n. And the way I find my coefficients is by exactly using this formula. I'm going to say, take whatever the kth derivative is. First time I do 0th derivative, then first, then second, then third, and on, and I divide by k factorial. So if I was to simplify that up just a little bit, I would see that I actually know again, oops, that no matter what derivative I take of my function here, when I plug in 0, I always get back 1. And so this here represents a modeling polynomial. It's just kind of been like scrunched together. If you imagine kind of squeezing both sides together at the same time, right? Squishing this thing in this way, you can kind of condense it all into this particular form. So this is really powerful, and it will allow me to make a lot of cool approximations with this. Notice then how well this thing begins to actually look. I could then start to say that, like, well, if I went to my calculator and I typed in something like, oops, let me scroll down there. If I typed in something like, please hold, I didn't realize this stuff would be on here. I go to my calculator and I type in something like e to the power of x, and then I started here writing out my polynomial, I could start to just build a polynomial that looks more and more and more like my function. And this formula here tells me exactly what the next term is. Notice if I want an x to the third, what number should be in front of it? Well, it should be 1 over 3 factorial, so that's 1 over 6, x to the power of 3. If I wanted x to the fourth, I'd have 1 over 4 factorial. That's 1 over 24. That should be x to the power of 4. 5 factorial, that'd be 1 over 120. And then that would be the coefficient x to the fifth. If I wanted to go up to the x to the sixth term, I'd have 1 over 6 factorial, which I think is that 720? And then times x to the power of 6. So like I could just keep going and going and going, and here's the cool part. When I hit the graph button, I can see not my picture because it's slightly off of the screen. But if I wait for the thing to stop spinning and thinking, then I can reset the picture. Here's my e to the x. Here's my modeling polynomial. Well, that's doing a pretty good job. And that's only x to the power of 6. Notice if I was able to keep going and going and going, I could get better and better and better. And then the goal would be to say that I could start to plug in, again, just about any number. Notice if I plug 1 in here, the red thing and the blue thing are almost the same. Notice I could even apply that in general here. I could state down here, this means if x is equal to 1, then f of 1 should be roughly the same as p sub n of 1. So f of 1 is equal to e to the first power. So that's just e. It's like 2.7-ish, right? And that should be roughly the same as going to my polynomial up here and replacing all of the x's with 1s. So that would be like 1 plus a half. It's not a half. And then going on and on and on, all the way up until I get to 1 over n factorial. Or that would be like dealing with the series, start at thing 0, stop at thing n, 1 over k factorial. Like, we could actually take a look at that to see if that actually is roughly the value of e. This is a really cool idea. Take a look at this. 1 plus 1 plus a half plus 1 over 3 factorial would be 1 over 6, 1 over 24, 1 over 120, 1 over 720. I know my factorials because I've done this for many semesters. 1 over 5040, right? Like I could just keep going and going and going, and when I hit enter, take a look at the value that I've created. I only went up to 8 factorial in the denominator, but if I look at what e to the 1 is, holy crap, we have the first 4 decimal places perfect, and we only had to go to 8 factorial in the denominator. What if we went to like 800 factorial? I wonder how accurate we could be. This is a really, really, really powerful idea, and it shows why we actually really can care about these sort of modeling polynomials from even like a computer science perspective. That we could say that, gosh, how is it that I could program something to spit out a value of e to a power? Well, if I can create a modeling polynomial that only requires that I add, subtract, multiply, divide, that's not too difficult. And I can actually state, yeah, this value will be pretty close. The only question that I have now would be, how would I know if it is going to be really close or just kind of close? Is there a way to judge that closeness? And that's stuff that we'll talk about more in the coming sections. In the next video, we'll take a look at a way we can slightly adapt this and some other examples we can use to try to practice and deepen our understanding.